Pratima and welcome to Planet Physiology. Today we will explore an interesting topic in respiratory physiology, dead space. I am sure this video will be very useful to all the physiology students to write a short note on dead space, and others definitely will be benefited by its concepts and the clinical applications. We shall cover this topic under the following headings: definition and normal values, types of dead space, measurement methods, importance of dead space, and clinical aspects. Let's start by understanding what is dead space. Dead space is defined as the volume of air that does not participate in gas exchange. In a normal healthy person, the conducting zone of the airways, that is up to 16th division of tracheobronchial tree, contains air that does not reach to the alveoli for gas exchange. So this contributes to dead space. In very simple terms, it is the wasted ventilation. Here is a representation of airway passage showing conducting zone and respiratory zone. Normally, a relaxed person breathes about 500 ml of air per breath, which we call it as tidal volume. Out of this, 150 ml remains in conducting zone and forms dead space volume. Since this is the anatomical region where gas exchange does not take place, it is called as anatomical dead space. So this is the first type of dead space, anatomical dead space. In some conditions, if alveoli are not properly perfused, for example, due to blood vessel blockage, the air in such alveoli cannot participate in gas exchange, and this also contributes to dead space, and this is called as alveolar dead space. So second type of dead space is alveolar dead space. In alveolar dead space, ventilation is wasted due to reduced or absent perfusion. The next type is physiological dead space. Physiological dead space is nothing but sum of anatomical and alveolar dead space. It is also referred to as total dead space. In a healthy person, alveolar dead space is 0 ml. So physiological dead space is equal to anatomical dead space, that is 150 ml. Now let's study how to measure dead space volume. Dead space can be estimated by different methods. The simplest estimation of dead space is by Radford's formula, where weight of a person in pounds gives the value of dead space directly. For example, if person weighs 68 kg, his weight in terms of pound is 150. Hence, his dead space is 150 ml. Next, relatively easy method to measure the dead space is by single breath nitrogen method, which is also called as Fowler's method. It is used to measure anatomical dead space. So let us study this method. Here the subject exhales completely and then takes a single deep breath of pure oxygen and exhales in nitrogen meter. The exhaled air is then analyzed for nitrogen concentration using nitrogen meter. The anatomical dead space is calculated based on the exhalation graph. So let's understand this graph. This initial part of the graph till this dotted line indicates inhalation of pure oxygen. Now the subject breathes out in nitrogen meter, which measures concentration of nitrogen and exhaled volume of the gas. As the subject begins to exhale, initially no nitrogen is detected because initial exhaled air comes from the tracheobronchial tree, and since the subject has inspired pure oxygen, it does not have any nitrogen in it. This is called as phase 1 of expiration graph. As the exhalation continues, nitrogen concentration rapidly increases and finally reaches to a plateau. So this brief phase where nitrogen concentration rises rapidly is called as phase 2. In this second phase, exhaled air is mixture of dead space in the tracheobronchial tree and the alveolar air. Hence, as more and more alveolar air contributes to the expired air, nitrogen concentration rises. In phase 3, nitrogen levels reach to the plateau, and now the entire exhaled air is coming from alveoli. So from this graph, dead space is calculated by adding volume of gas exhaled during phase 1 and half of the volume of phase 2. Now coming to the last method, single breath carbon dioxide method. It uses Bohr's equation to estimate physiological dead space by comparing carbon dioxide levels in alveolar and the expired air. Carbon dioxide in the inspired air is negligible, it can be ignored and formula is modified accordingly. So for this method, we need data on partial pressure of carbon dioxide in expired air as well as in the alveolar air and the tidal volume. As ventilation perfusion ratio differs in different lung units, in health and in disease, alveolar PCO2 is not a single value. Hence, in practice, the arterial partial pressure of carbon dioxide is used as an estimate of average alveolar partial pressure of carbon dioxide. The dead space is calculated as tidal volume into alveolar PCO2 minus expired PCO2 divided by alveolar PCO2. Normally, tidal volume is 500 ml, arterial PCO2 is 40 mm of mercury and expired air PCO2 is 28 mm of mercury. So by substituting these values in Bohr's equation, we get dead space as 150 ml. If you are interested to know how much exactly is the alveolar dead space, you can simply subtract anatomical dead space from physiological dead space. Bohr's equation method is mainly measuring the physiological dead space. This equation also can be used to measure anatomical dead space by replacing arterial PCO2 with alveolar PCO2, where PCO2 of the last 10 ml of the expired gas is considered as alveolar PCO2. Okay, we have studied that dead space air does not participate in gas exchange. So think about it. Is this 150 ml of dead space air completely waste or does it serve some purpose? Yes, you are right. Dead space is not just a wasted air, it has important functions to perform. First and most obvious function of dead space is protection or the protective function. Mucus and the nasal hairs filter out dust and pollutants and then they are removed by the ciliary movements which are lining the tracheobronchial tree. As the inspired air passes through the conducting zone, it is warmed to the body temperature. This protects alveolar damage by the cold air and also improves oxygen uptake by increasing affinity of hemoglobin for the oxygen. Inspired air is also humidified during its passage in the dead space. Thus, dead space air protects delicate lung tissues from dryness, cold air and particulate matter. Next function is its role in carbon dioxide regulation. Dead space slows carbon dioxide elimination, preventing sudden drops in partial pressure of carbon dioxide in blood, that is hypocapnia. This prevents respiratory alkalosis and stabilizes blood pH. Next function is optimizing gas exchange timing. It is the function of both dead space as well as functional residual capacity. Gradual mixing of fresh and alveolar air ensures efficient gas exchange. It prevents immediate exhalation of oxygen-rich air, optimizing diffusion gradient. And the last function is its role in exercise. During mild exercise, increased tidal volume compensates for dead space, ensuring efficient gas exchange without excessive breathing efforts or the work of breathing. Okay. Now let's see implications of dead space in diseases. Conditions like pulmonary embolism, emphysema or respiratory distress syndrome increase alveolar dead space. This causes ventilation perfusion mismatch leading to hypoxia and increase in work of breathing. Here is a thought question for you. What is mechanical or external dead space? Can you give some examples of it? And what effects does it have on the body? Post your answers in the comments below. Thank you for watching and see you in the next video. If you enjoy my presentations, press the like button and share it with your friends. For more such videos, subscribe my channel and click the bell icon. Thank you for watching and see you in the next video.